So yeah, in the previous section, we did already most of the hard work. That means implementing this custom collate function. In this section, we are now using the instruction dataset, the PyTorch dataset that we created earlier, and this custom collate function, put them together, and then we have a way to load the training and validation data for the actual fine-tuning. So we will begin with defining the device that we will be using. So everything in this notebook from now on will also work on a GPU if you have one, for example, a CUDA GPU. You can also replace this with MPS if you have Mac, which supports Apple Silicon. Now, I think still, based on my last experiments, you get slightly different numbers if you use the MPS device. So MPS is the GPU in the Apple Silicon chips. So it's basically on your own. I wouldn't say risk, but if you are open to get slightly different results, you might want to experiment with MPS, which will be faster than CPU if you're using a Mac. So here I will be running it on the CPU though, so that the values shown here should be similar to what you're getting on a GPU or a different type of CPU. And then one thing I wanted to also do first is defining defining a custom collate function, or a customized one. So we defined the custom collate function before, and remember there were a few settings we had. For example, padding token ID, we don't need to change that. The ignore index, we don't need to change, but we maybe want to change the device and the allowed max length. And so this is just like a Python basic. We just use func tools to make use the partial here to make a customized version of that. So that means it's just like a Python basic. That means if I use this one now, so if I call this one as a function, it will have the default values for the allowed max length of 1024, and it will use the device we define here. So that is all we are doing. It's really just like a Python basic. If you don't want to do it like that, you can also just go up here and modify those values here, up to you. So, but that's usually how I prefer pre-filling function arguments with partial. So that's what we're doing here. And then we are ready to use the DataLoader. So here, that's just the PyTorch DataLoader that we used in chapters 5 and 6. We will again use 0 workers for maximum compatibility. We use a batch size of 8, the random seed for the shuffling. And so here I'm creating the training data set by passing the train data that we just generated earlier in this chapter to the instruction dataset class that we defined above, together with the tokenizer. And this then goes into the DataLoader. And so everything you are seeing here, all these settings except one, are the same that we used in chapters 5 and 6. So I'm not explaining again what drop last means, and also what the batch size means. You should be, I guess, already be familiar with that. What's new though is the custom collate here. So here we plug in our customized version, which uses max length of 1024, and then also the device, in this case, the CPU. So yeah, so that's what I'm doing here. I'm setting it up. For some reason, it's complaining. So let me go up here. Maybe I made a typo or did not execute it. Yeah, I did not execute this cell. So this is the instruction data set from the previous section. Now it should work. Yep, so there we go. So this is our training loader. And we can do the same thing for the validation and the test set. So here, the same thing. The only difference is that we don't need to shuffle and we don't need to drop the last entry here. So, but otherwise, similar to what we have done in chapter 6, same code as for the training set. Okay, and it's not a bad idea to take a look at like the results, that what the DataLoader outputs, just to make sure everything looks okay. So like usually I just tend to iterate over the data set, doing the iteration just to make sure everything looks okay. Remember now that each batch has its own longest entry. So one batch might have size 61, so 61 tokens as the longest entry. Some batches have 76, 73, and so forth. And yeah, that doesn't matter, because what we are doing is we are training the model to predict the next token. So we are not, like in chapter 6, fixated on a certain token position. We are really more general. We have a free-form answer, and it can have different lengths. And it doesn't really matter how many padding tokens we have also, because we have this -100 here to ignore excessive padding in our loss function. However, we still have to make sure that each entry in the batch itself has the same length. Otherwise, we can't create a tensor. Right, so that's looking good here. So we can see about most of the example have about like 70, 80 tokens. So it's a very small data set, 1,100 entries, and each example is also very short. I did that by design also to speed up the training. In addition to that, also maybe not a bad idea to take a look at one of these entries to see that they look okay. So we can see this is the first training example. So here we see that, if I iterate through this, inputs will default to the last inputs targets in the training loader. So we are looking at the first example of the last batch. So I said, the first example in the last batch. So we are looking at the first row in this one. And so let me just do the length here. I can also do shape, but you can see that's 69. And we have the padding tokens as we would expect. Let's also check the targets corresponding to this one. So we can see here it's shifted by one position, right? So this is here. So that's looking good. And for the padding tokens, we still have that one padding token that we want to keep. So the model learns when to stop generating text via our generate function, text generate function. And then here the other ones, we have -100 because we don't want to have them influencing the loss during training because they're really just placeholders. And this is our data loader now. It works, looks good. And in the next section, we will put it to action. Or maybe not in the next section, but in a few sections, because we still have to load the model itself, and then we can fine-tune this.
Get this book at Manning.com.